Dear students, myself Sanjeev Goyal. I am working as senior lecturer at Government Polytechnic College, Bathinda. Today our topic of discussion is frequency modulators. This topic is from subject PC, Principles of Communication Engineering, from third semester ECE. First of all, modulators are the circuits designed to produce the modulated output. That means it vary any one of the carrier parameter such as phase, frequency, amplitude in accordance with the instantaneous value of the modulating signal. So, in the process of modulation, any one of the parameter, either frequency, phase or amplitude of carrier varies in accordance with the instantaneous value of the modulating signal. The circuit that generates FM waves are either directly or indirectly are known as FM modulators. That means it varies the carrier frequency in accordance with the modulating signal. So, our purpose is to vary the frequency of the carrier signal RF signal in accordance with the instantaneous value of modulating signal either directly or indirectly. So, accordingly, frequency modulators are of two types. First are direct methods of FM generation and then are indirect method of FM generations. First of all, direct methods. In direct methods, first method is varactor diode modulator. What is the varactor diode? Varactor diode is also called as vari-cap diode. Its capacitance is proportional to the amount of reverse bias voltage across the PN junction. So, when reverse bias voltage is increased across this PN junction, its depletion region becomes wider and wider. As this diagram shows, there are two regions P and N. When this P and N junction is reverse biased, that is P is connected to negative and N is connected to positive, its depletion region becomes wider and wider. So, the depletion region increases and its capacitance decreases. Conversely, when the reverse bias voltage decreased, the depletion region width becomes narrow. So, capacitance increases in this case. So, when reverse bias voltage increases, depletion region width increases and capacitance decreases, whereas in case of reverse bias voltage decreased, depletion region becomes narrower and capacitance value increases. So, it is proved that varactor is used in reverse bias conditions only. Varactor diodes are used in reverse bias conditions only. We consider a relationship between a varactor diode and a conventional capacitor. A reverse biased varactor diode is similar to a capacitor. When a PN junction semiconductors combine together, a small depletion region is formed. This is due to the diffusion of minority carriers. The positive and negative charges occupy N and P sides of the junction respectively. This is just like a capacitor in which there are two plates, one is positive, other one is negative, and there is a dielectric region, dielectric space between two plates. Similarly, in case of a reverse bias junction semiconductor diode, PN diode, one side is positive, other side is negative, and in between there is a depletion region. The amount of internal junction capacitance can be calculated by the capacitance formula C is equal to rho A upon D, where A is the cross sectional area of capacitor and D is the width of the depletion region. So, according to this relation, as depletion region width increases, value of capacitance decreases, whereas as depletion region width decreases, value of capacitance increases. That means, C is inversely proportional to the width of the depletion region. So, from the above formula we know that the varactor capacitance is inversely proportional to the width of depletion region, that is distance between plates in parallel plate capacitor. If the area A is kept constant, a small reverse voltage will produce a small depletion region. Small depletion region means a large capacitor. In other words, an increase in reverse voltage results in increase in the depletion region and results in small capacitance. This variation in supply varies the junction capacitance of the varactor diode as its capacitance varies linearly with the applied bias, that is C is equal to 1 upon under root V. C is equal to 1 upon under root V, where V is the applied reverse bias DC voltage. So, as the capacitance of varactor diode change, the oscillator frequency will also change, as F is equal to 1 upon 2 pi under root L CV. CV means capacitance, junction capacitance of reverse biased varactor diode, and CB is the RF capacitance. So, as V increases, according to this, as V increases, value of CV decreases, F increases, or as V decreases, V is the applied reverse voltage, decreases, CV increases, capacitance of varactor diode increases, and F according to this relation decreases, and this change in frequency produces FM. This is the equivalent circuit of varactor diode. So, varactor diode can be considered as a capacitor and a resistor connected in series. The junction capacitance is the capacitance between P and N junctions, where RS is the sum of bulk resistance. So, this is a diagram of varactor diode. This is a varactor diode connected in the reverse bias condition. This is the applied voltage to keep this diode always reverse biased. This is VM modulating signal is applied here, according to which the biasing of diode changes and it gives a variable capacitance. This variable diode capacitor is connected across a LC oscillator. So, in this circuit, varactor diode is reverse biased with voltage Vs. Modulating voltage Mt is applied through the primary of input transformer. Modulating voltage changes the bias to varactor diode. It changes the capacitance of varactor diode. This change affects the overall capacitance of tuned circuit having L1 and C1. The frequency generated by this tuned circuit changes as modulating voltage Vmt changes. Radio frequency coil RFC, this is RFC is the radio frequency coil, is used to prevent the oscillator output to go through secondary and bias voltage. This RFC is used to prevent the oscillations to come back into the input. C2 is the, this C2 is the isolates DC bias voltage from tank circuit or tuned circuit. R1 limits the bias current. Its value is selected to provide proper bias current, which will used for unmodulated carrier. Second type of direct modulator for FM is voltage controlled oscillator VCO. As the name indicates, it is a oscillator whose output is controlled by the applied voltage, or we can say that it is the oscillator whose frequency is controlled by the applied input voltage. This is also a direct method of FM generation. In a VCO, the oscillation frequency varies linearly with the control voltage or applied voltage. A voltage controlled oscillator is an oscillator whose output frequency is proportional to the input voltage. So, it gives a variable frequency which is proportional to the input voltage. It really is a frequency modulator. Typically, these devices are not able to produce large frequency deviations. VCOs are also used in voltage to frequency conversion applications, because its input is a voltage and its output is a variable frequency. In voltage controlled oscillator, the frequency of output signal is proportional to the input signal. Voltage controlled oscillators are used to vary the carrier frequency of the carrier signal with the baseband signal amplitude. This is the block diagram of FM generation by using voltage control oscillator. This is a VCO, voltage control oscillator. Input to this voltage control oscillator is a modulating signal or baseband signal MT. To stabilize its output, we have a mixture. In mixture, there are two inputs, one is of the VCO, other one is from the crystal controlled oscillator, because crystal oscillator is always a stable oscillator. These two frequencies are mixed in mixture and are applied to frequency discriminator. Frequency discriminator is a frequency to voltage converter. It gives a voltage output depending upon the output of mixture. If both the frequencies are same, that is VCO and crystal oscillator frequencies are same, its output is 0, it's okay. If VCO frequency is more than crystal oscillator frequency or less than crystal oscillator frequency, mixture gives a positive or negative DC voltage which is applied to VCO to correct its output. So, we get a frequency stabilized FM wave. We can generate the required FM signal from a VCO by using message signal as the control voltage. VCO can be constructed by using either by using integrator or hysteric comparator, but the most common hysteric comparator is a Schmidt trigger. So, this is a VCO concept. In this the voltage varies, so it gives a triangular wave. So, in VCO we get a variable oscillator frequency depending upon the input voltage. So, it converts voltage into frequency. To construct VCO, either a Schmidt trigger or a integrator is used. So, we get a triangular wave whose output is vary between E0 and minus E0, and depending upon its output we get a variable frequency. And third direct method is reactance modulator. First one is varactor diode modulator, second one is VCO. VCO is itself a FM modulator because it gives a variable frequency depending upon the input voltage, and third one is the reactance modulator. This circuit is basic FET reactance modulator. It behaves as a 3-terminal reactance. It can be connected across a tank circuit oscillator to produce frequency modulation. So, as in the case of varactor diode modulator, here also this variable reactive device is connected across a tank circuit or tuned circuit to give a variable frequency. It can be made, this reactance can be made either inductive or capacitive by simply changing the position of the components. The modulating voltage is supplied to the variable reactance device. As the value of modulating voltage changes, the reactance of the device also changes. This will change the frequency of oscillator to produce FM wave. The modulating voltage is applied between the two terminals of the FET. The value of the value of the reactance is proportional to the transconductance of the device. This value can be made to depend on the gate bias, as in case of FET there are 3 terminals, drain, gate and source. So, the value of transconductance depends upon the gate bias and its variation. Any amplifying device such as FET, bipolar transistor or vacuum tube is used as a variable reactance device. This is a diagram of reactance modulator. In this case, a FET is used here having 3 terminals, gate, source and drain. Modulating signal is applied here between A and A dash, that is V. This is Vg is the gate bias, gate voltage, Ib is the base current, and I is the drain current. So the parameters here are: Z is the impedance, V is the applied modulating voltage, Vg is the gate bias, Ib is the base base current bias, and I is the drain current. Here two components are used are C and R, and by interchanging these two components we can get any reactance either inductive or capacitive. The impedance Z is to be measured between terminals A and A dash. A voltage V is applied to these two terminals A and A dash. Current I, that is drain current I, is changes due to the voltage V is calculated by using simple formula Z is equal to V upon I. To obtain a pure reactance, there are some conditions. To get a pure reactance, there are some assumptions are to be made. First is bias current IB must be negligible as compared to drain current. So this current IB must be negligible as compared to drain current I. Second is impedance of the bias network must be very large to ignore it. The drain to gate impedance must be greater than gate to source impedance. So drain to gate impedance, that is XC, must be greater than gate to source impedance R. So as assumptions are made, XC must be greater than 5 times R. So according to this we get Vg. Vg is the gate voltage. Vg is equal to IB into R. IB is the bias current, or it is equal to R into V upon R minus J XC. The FET drain current relation is I is equal to Gm into Vg, where Gm is the trans conductance. So Gm Vg is equal to IB R into V divided by R minus J XC. So first of all we get the value of Vg. Vg is a voltage across this gate and source junction. This is equal to IB into R, whereas IB is equal to V upon R minus J XC. Then we from Vg we get ID, drain current, that is Gm into Vg, where Gm is the trans conductance. So Gm into Vg. Vg's value is R into V divided by R minus J XC. So we get Gm into R into V divided by R minus J XC. Therefore, resulting impedance at A and A dash is Z. Z is equal to V upon I. So I value is Gm into RV divided by R minus J XC. So V divided by Gm into RV divided by R minus J XC. V and V are cancelled. So we get 1 upon Gm into R minus J XC. So 1 upon Gm, divide this R minus J XC by R. So we get 1 upon Gm into 1 minus J XC upon R. Again the value of Z is equal to 1 upon Gm. Gm is the trans conductance of FET into 1 minus J XC upon R. As we already assumed that XC is very greater than R. So XC upon R is very greater than 1. So 1 may be neglected. So Z is equal to minus J XC divided by Gm into R. This impedance is capacitive reactance and it may be rewritten as X equivalent. Z may be rewritten as X equivalent. Its magnitude is XC upon Gm into R. Because X equivalent is XC into Gm into R, X equivalent is equal to 1 Xc is equal to 1 upon 2 pi f. So, 2 pi Fc. So, it becomes 1 upon 2 pi f Gm into Rc. This Gm into Rc is written as C equivalent. So, from this expression we get that this arrangement of FET acts as a variable capacitive reactance. Under such conditions, the input impedance of the device at terminals A and A dash is pure reactance, that is C equivalent is equal to Gm into Rc. The equivalent capacitance depends upon the device transconductance, and the device transconductance varied with the bias voltage. The capacitance can be originally adjusted to any value within the reason by varying the components R and C. The expression that is Gm into Rc, here we get the Gm into Rc, which is written as C equivalent. The expression Gm into Rc has the correct dimensions of capacitance as the units of Gm is Siemens or mho, whereas units of R are ohms. So, mho and ohms are cancelled and units of C are farad. So, Gm into Rc, ohm multiplied by Siemens multiplied by farad, and ultimately we get farad. Farad is the unit of capacitance. So, the expression Gm into Rc represents a capacitance whose value depends upon the Gm. Gm is the transconductance of the device, and the value of Gm depends upon the applied voltage. It is already stated that the gate to drain voltage impedance must be much larger than the gate to source impedance. Then the R is not much less than X. If the R is not much less than Xc, so we assume that Xc is very greater than R, the gate voltage will no longer be exactly 90 degree out of phase with applied voltage V. So, Xc, there are two assumptions are made. Bias current IB must be negligible as compared to drain current I, and second one is Xc must be very greater than R. By interchanging R and C and selecting the value of R such that R is very greater than Xc, already we assume that Xc is very greater than R. Here we discuss that by interchanging the values of R and C in this first diagram, interchanging R and C, and by making R very greater than Xc, we get variable inductive reactance. So, either capacitive or inductive, this variable reactive device is connected across a tuned circuit whose frequency is equal to 1 upon 2 pi under root L into C, and plus this variable reactive device. So, we get a variable frequency across the tank circuit. There are 4 different arrangements of the reactance modulator. The drain current must be greater than the bias network current in all the arrangement. That means I must be very greater than IB. So, IB must be negligible. The arrangement we already discussed, RC capacitive. In this case, gate to drain is C, gate to source is R, and Xc is very greater than R, and we get variable capacitive reactance, that is C equivalent, that is equal to Gm into Rc. Other arrangement is gate to drain is R, gate to source is C, and R is very greater than C. In this case, we get variable inductive reactance L equivalent, that is equal to Rc into Gm, Rc divided by Gm. Or there are two other arrangements, that is RL, we get capacitive or inductive reactance. In all these cases, the reactance either inductive or capacitive depends upon the transconductance of the device Gm, and this transconductance Gm depends upon the applied voltage. So, when we vary the applied voltage, the Gm varies. Accordingly, the reactance varies, either it is C equivalent or L equivalent. This variable reactance is connected across a tuned circuit whose frequency is equal to 1 upon 2 pi under root L into C. So, accordingly, either it is inductive or capacitive, overall frequency of the tank circuit varies. So, in this case, with the applied voltage, the frequency varies and we get a FM output. So, these are the direct methods of frequency modulation, that are varactor diode modulator, VCO, that is voltage controlled oscillator, and then reactance modulator. Then next is the Armstrong method of FM generation. This is the indirect method of frequency modulation. What is the need of indirect method? In all the methods we have discussed earlier, that is varactor diode modulator, either VCO or reactance modulator, we are using a LC tank circuit or tuned circuit across a circuit. We cannot use the crystal oscillator because crystal oscillator cannot be frequency modulated. The direct modulators are based on LC oscillator, which is not stable enough for communications or broadcast purposes. So, we are using LC oscillators, but LC oscillators are not stable enough for communication or broadcast purposes. This requires stabilization of the reactance modulator with some extra circuit complexity. To get stability, we have to make it stable and we increase its complexity. There is another method to generate FM through phase modulator, where a crystal oscillator can be used. So, therefore, this method is known as a indirect method, because in this case FM is generated through phase modulation and by using a crystal oscillator. The most convenient frequency for the crystal oscillator and phase modulation is nearly 1 megahertz. Transmitting frequencies are normally much higher than this, but the frequencies are much higher than this. So, frequency multiplication must be used. Mixing of the FM signal changes the center frequency only. So, frequency multiplication multiplies center frequency and deviation equally. A narrow band FM signal is generated using balance modulator, which is used to modulate, say, crystal controlled oscillator. Maximum frequency deviation in this case is kept constant and very small to keep the validity of this equation. So, there are some requirements, that one is that the frequency must be near 1 megahertz, but whereas transmitting frequencies are much higher than this frequency. So, in this case frequency multiplication must be used. So, frequency multiplication is applied to center frequency as well as to deviation. We get a narrow band FM signal, which is used to used in balance modulator to modulate a crystal controlled oscillator. In this case, the maximum frequency deviation is kept constant and small to keep the validity of this equation valid. Ultimately, we get a wideband FM signal by using frequency multiplication of narrowband FM signal. Phase noise increases as a function of frequency multiplied by factor n. This indirect method has high frequency stability because of use of crystal oscillator for carrier generation. Now that in FM, the carrier frequency deviation is proportional to modulating voltage as well as modulating frequency. So, in phase modulation, frequency deviation is proportional to modulating voltage Vm as well as modulating frequency Fm, but in FM the frequency deviation is proportional to only Vm modulating voltage. To overcome this, or to obtain FM from PM, integrator is used. Integrator will attenuate the high frequency modulating signal, but there is no change in the amplitude of low frequency modulating signal. Output of filter is added to